We are now recording, and I'm going to get the slideshow set up for where I left off last time. But where we did last time, what we did last time, we went over the syllabus and then went over my locator card, when I'm where, you know, and that type of thing. Oh, and the locator card is also under that same topic in Blackboard, and I can't remember what it's called. It's one that has an and in it. It's this and other things or something like that. So look for that. And then all the PowerPoints are there if you want to print those out to take notes on or whatever. But then the YouTube video link will then take you any time to go back through that. Okay? So last time we got started in Chapter 5 because from the syllabus, and this was developed by the state, not by me, they said that we would be talking about forces. So Chapter 5 is talking about forces, and we just barely got started on it by the time we got everything else. We also started upstairs. Did anyone go upstairs first and come back down, or did you know it was changed? Oh, okay, good. I hope the secretary wasn't in. I don't know if the sign's still up upstairs or not. I hope there's no one up there sitting and waiting, but we'll just assume not. Okay, now this computer that I use is what they call a tablet PC. That means it has an ionizing pen and I can write on it, and that's what I do. Now, they recommended this book because the other school in the state that teaches this, I think it may be Wallace Hansful or somewhere, this is the book they use, so this is the one we did. When I got it, I found out that, I got it the Friday before the class started on Wednesday. I found out they don't really have very good PowerPoints. They have some of the illustrations, and that's about all. It's image PowerPoint, but not lecture PowerPoint. So, Jeremiah? Okay. All right, we've got everybody that was here last time plus one. So, I don't know if the others are coming or not. There are one or two others, I think, that are paid, maybe just one other that's paid. So I would think she would show up, but the others were unpaid last time I looked, so I'm not sure they're coming. I assume they'll leave the class running with this smaller class because they're trying to get the program started, but that's just an assumption. They haven't canceled it yet, so I don't know. We'll see. All right, so all but one of you was here last time, so let's get going. Any questions from what we did last time? Okay. I take it not many of you have a book. I only see one, two, maybe three. Okay. Oh, you got it on. Good. So try to cover as much as I can on here. This is not a particularly good slide for what we're doing now, because this slide comes up a couple pages over. But like I said, the figures are few and far between. There's no room to work on that one, so I turned to this one. And we're doing example 2 at the top of page 127. It has nothing to do really with this picture. Sorry about that. Here's the question. What force is necessary to produce an acceleration of 2.00 cubic feet per second? And again, when you're solving problems, which physics is about solving problems, we're looking for force. Let me get my pen. Okay. We're looking for force. That's what the question is. What force is necessary to produce an acceleration? So they're giving us an acceleration of 2.00 feet per second squared. Okay? On a mass, well, here's the mass, of 3.00 slugs. Okay, yuck. You'll never really see a problem like this, okay, for a couple of reasons. I'll give you the reasons now. Some of you who were here before probably already know what's coming. First, let me say this. Is this better than last time with the wiggling? I still see it wiggling some, but I don't know if it's vibration or what, but it just seems like it's got a little jiggle to it. And it's not the board, it's, I think, the projector. Okay. When they give a lot of digits like this, that means that it's very precise. The acceleration is 2.00 feet per second squared. That means it's not just 2 or 2.75, which rounds to 2. 1.75, which rounds to 2, or 2.1, which would round to 2. This is 2.00 to the nearest hundredth of a foot per second squared. Now, again, that's not really very realistic, because how many things can you measure accelerations with that kind of precision? But for the purpose of here, and the mass, I forgot to put down the unit of slugs. Okay. Does anyone remember what a slug is? It's the U.S. customary, sometimes called the British or English unit system unit for mass. We never use it, ever use it. That's why I say you'll never really see a problem like this. But again, that's not 3.01 slug, 3.00 slug. That's very, very precise. It's sort of beside the point. What they're looking for is what is the force necessary to give that mass an acceleration. Anyone know the formula to tie those three things together? If you were here last time, you should remember it. What was it? Force equal mass times acceleration. Now, I always called that the net force. They don't say that here, but since that's the only thing in the problem, that is the net force, okay? So all we do is plug in 3.00 slugs. Again, you'll never see that in a real-life problem. Times the acceleration of 2.00 feet per second squared. Oh, here's the other thing I was going to say. If any of you are puzzling over what a square second is, don't worry about that. What that is a foot per second per second. It's just a shorthand way of writing that. You don't have to put 2 bars and 2 seconds down there. It's foot per second squared. There's no such thing as a square second. Okay, that's just a shorthand. And this would give us what? The math is easy. What's that? 6.00, since you have 3 digits coming in, 3 digits going out. Okay? Now, what's the U.S. customary unit for force? When I stood on the scale this morning. And was sadly disappointed. Pounds, exactly. That's the unit of force in the U.S. customary system. That's a slug foot per second squared. Okay? Again, you never use slugs. We would use pound. That's the force necessary to give a 3-slug mass an acceleration of 2 feet per second squared. Okay? 6 pounds. 6.00 pounds. All right. Somewhat of an artificial problem, but it still uses the formula and shows you how to put it together. Okay, any questions on that? All right, erase that. Let's go to example 3. Find the acceleration produced by a force of 500 newtons. So we're looking for acceleration, that's the unknown in this problem, produced by a force of 500 newtons. Now, they do something here that's a little strange seeming. They put a horizontal bar over the second zero of the 500. Does anyone know what that means? That means that zero is significant. This isn't 493 rounded to 500. This isn't, 507 round to 500. This is 500 rounded to the nearest Newton, okay, to the zero. So that says that zero is significant. You have 3 significant digits there again. Okay? Of course, anything in between it and the other is significant as well. Applied to a mass, so here they give you the mass of 20.0 kilograms. Where did my screen go? There it is. 20.0 kilograms. See, in the SI system, System International, kilogram is a mass unit. Newton is the force unit. Okay? We talked about that last time. Okay? Now, how do we solve that for acceleration? What's our base formula? Same one we used before. What was it? Force equal mass times acceleration. Now, you can do it either one of 2 ways. Solve this for acceleration, since that's the unknown here. And how do you solve that equation for acceleration? Divide by mass. Divide both sides by mass. And that produces acceleration, because the masses divide out here, equal force per unit mass, which would be, plugging in, 500 newtons divided by 20.0 kilograms. Now, when I'm doing this, I like to put down what the basic units for newtons are. And I don't know if you remember this from before, but a newton is a kilogram meter per second squared. I like to go on, instead of writing newtons, write down what it is in the base units. Kilogram meter per second squared. Okay? And then when you do that, you notice the kilograms will cancel out. Okay? And 20 will go into 500. Anyone do that in your head? 20 go in 50 twice. 2 times 20 is 40. Remainder 10. Bring down the 0. 20 will go into that 100 5 times. Okay? Yeah. And what units do we have left? Oh, we have 3 digits, so put a 0.0 meters per second squared, because that's all that's left when the kilograms go out. And that's an excellent unit for acceleration. Distance per time, meters per second squared. Okay? And you'll see that's exactly what they got in the book. All right. Now, for those who don't have books, or your plans to get one, or I take it, I'm guessing the ebooks are a little cheaper. Is that right? Okay. So if you've got one, that would be cheaper. In the book, you have these problems, and these are very similar to the 3 we've done already. 1 we did last time, 2 we did today. But there are 8 problems at the bottom of page 127. Find the total force necessary to give each mass the acceleration. It has a variety of units. I don't think you have to do them all, but do a few of those just so you get used to them. Then that's 1 through 8. 9 through 15, find the acceleration of each mass given the total force, just like the ones we just did. And then the rest of those, mix them up a little bit. So do some of 9 through 16, and then some of 17 to 33. I'll let you decide how much you want to do. There's no real requirement to doing. I think some of them are so similar it probably would be not that beneficial to do them all, but you decide that. Now let me check here and see in the back of the book. Okay. Chapter 5, page 127 and 128. Yeah. 5.2, it looks like they have the odd number exercises in the back, the answers to the odd number exercises in the back. I can't swear they have them all, but it looks like they have all of them 1 through 33. Yeah. So they do have the odd numbers in the back. So What I would recommend is do any of the odds 1 through 7, any of the odds 9 through 15. You choose how many of those that you need to do to get the concept down, and any of the odds 17 to 33. Okay. All right, any questions on that? So it looks like they do have odd number answers in the back. Now, when we were talking about forces in general, what unit do we have in U.S. customary for force? English or British system? Stood on the scale this morning? Say again? Pounds, exactly. Okay? So therefore, when you're talking about weight, you're talking about forces. Okay? Now, and remember, I kept saying, when I use this formula, I always say net force. Okay? And when I'm standing on the scales this morning, that was sort of the net force. So I wasn't any additional forces. I wasn't pushing or pulling on anything else. That was just the force of gravity pulling down on me. So therefore, my weight was pushing down on the spring in the scales, and it was giving me a weight. Okay? So that was a net force. But quite often, the weight is not the net force. Okay? That would be a variety. I gave the example last time of an airplane flying at 500 miles per hour, a jet plane. What's the net force acting on it? Well, if it's going at a constant speed, level flight, no net force because it's not accelerating. Okay? There's zero net force because there's zero acceleration. Does that mean the plane has no weight? Of course it has weight. Jet planes weigh a lot, a whole lot. So what we use is a formula very similar to this one when we're talking about weight. And here's what that formula is. Okay? The weight is, in this book, called the force of weight, I guess you say. In other books I've taught from, and I think I will, well, there it is right there. There is the weight of the object. That's the weight of gravity pulling down on that block that's sitting on the table. Okay? That is what we call that. Other books I've used have just merely called this little w for weight. Okay? I'll sometimes revert to that. I'll try to always use F sub w. Okay? That's the force due to weight. Others might use, in case you ever see this, F sub g, which is the force due to gravity. That is the weight. So all these three terms mean the same thing. F sub w, F sub g, and just a little w, that means weight. Okay? Now, because they're forces, the same units, pounds or newtons, and they would be, a pound is a slug foot per second squared. That's a pound. Okay? And a newton is a kilogram meter per second squared. That's the unit for newton. Okay? So what's the formula for that weight? It has a mass, and the mass would be either in slugs or kilograms. Okay? So it's mass of the object times, let me write it here, mass of the object times the acceleration due to gravity. Now, the acceleration due to gravity is this symbol we call g. Okay? Now, on the surface of the planet of Earth, we're going to be on Earth most of the time, right? Surface of the planet, g is either 32 feet per second squared, that would go with this unit, or 9.8 meters per second squared. That would go with newtons, okay, and kilograms and meters, okay? Now, if any of you have a calculator, you'll see that, well, whether you have a calculator or not, I guess you can see it. If you think about it, how long is a foot? 3 feet make a yard. A yard is approximately the distance from your nose to an outstretched fingertip. That's about a yard. A meter is just a little bit further than that. It's the opposite ear to the outside arm, approximately, okay? Most doorknobs are about a meter off the floor. That's what a meter is. Almost a yard, a little bit more than a yard, okay? So therefore, there's going to be a little bit more than 3 feet per yard. Per meter. There's exactly 3 feet per yard, a little more than 3 feet per meter. And if you'll notice here, if you take this number and divide it by that number, you'll get a number very close to 3, a little bit greater than 3. If anyone has a calculator, do it. Does anyone have one on them? 32 divided by 9.8. It's going to be about 3.3 approximately, but is that right?
You said to be what?
About 3.3. 32 divided by 9.8.
Is 3.26.
3.22?
26.
26, okay,
Yeah.
close to 3.3.
Yeah.
So, if you think about it, this distance here is about 0.26 of a foot, right? That's about 3 inches or so, 4 inches, and that's pretty close to a third of a foot, okay? Between a quarter and a third of a foot. 3 inches would be a quarter of a foot, 4 inches would be a third of a foot. So yeah, right in between those two. So here is the formula for weight, okay? The force due to weight, let me erase all this other stuff so you can focus on here. Force due to weight is equal to mg. M is the mass in the appropriate units, slugs or kilograms, and g is the acceleration due to gravity in the appropriate unit, 32 feet per second squared or 9.8 meters per second squared. Because everywhere on the surface of the earth, the acceleration due to gravity is very close to the same. If you're at the top of Mount Everest, you're not far off from where you'd be if you're in the bottom of the Dead Sea Valley. Okay? Anywhere on the surface of the earth is very close to 9.8 meters per second squared or 32 feet per second squared. Now, if you get way above the surface of the earth, like going into outer space, the acceleration falls off. Okay? So your weight decreases, right? Those astronauts out there, they float around as if they were weightless. They're not really. They still have a little weight, but it's just so very, very little. Okay? I think one of the astronauts, when he was standing on the surface of the moon, which has about a sixth of the acceleration due to gravity as the Earth does, because the moon's smaller, less dense, all these things, I think he hit a golf ball and just sent that flying because the acceleration due to gravity is so much less. Okay? So, again, F sub W is weight. Okay? Okay, M is mass, just like it was before. And G is acceleration due to gravity. And actually, let me correct, because this book uses 9.80 to the nearest 3 decimal significant digit meters per second squared, and they use 32.2 feet per second squared. Okay? So that would be probably a little bit less. Okay? Now what they term that, they call this the metric unit, the 9.8, the metric unit. I would call it the SI unit. Okay? More precise. And then the other is called the US unit. So they're not calling it British or English unit anymore. Okay? So let's look at some data here. What you're given, find the weight of 5 kilograms. Okay? We're looking for weight. That's F sub W. That's our unknown here. And what they're giving is of 5.00 kilograms. Now, what is a kilogram a measure of? What quantity is that you would measure with kilograms? mass. Kilogram is a mass unit. Pound is a weight unit. Newton's a weight unit. Slug's a mass unit. You know, gram is a mass unit. Okay? So this is going to be your mass. Okay? There's your formula. And guess what? They didn't give you G, did they? But here's what we're going to do. We're going to assume that you're on the surface of the earth. I mean, where else are you going to be? We're not going to be in outer space, okay? We're going to be on the surface of the earth. So we're going to assume the G for the SI units, or they call it metric unit. What G would we use? 9.80, okay? They use 3 digits, we'll use 3 digits. So your G we're going to use of 9.80 meters per second squared. So what would be the weight? F sub W is equal to, plug in your mass, there's your mass. Plugging in this formula. F sub W is equal to mg. Your mass is 5.00 kilograms. And G is, you'll use the metric unit or the SI unit, 9.80 meters per second squared. Okay? Now, that's going to be something less than 50. 49 point, second? 49 on the nose, isn't it? Yeah, 49.0 unit. Newton, exactly. A kilogram meter per second squared is a Newton. SI unit for weight or force is Newton. 49 newtons. Okay? 49.0 newtons. Okay? That's 1 kilogram meter per second squared. Okay? All right, for me to erase. Find the weight of 12.0 slugs. So we're looking for weight. Weight is F sub W. That's our unknown here. And they give us 12.0 slugs. What is that a measure of? Besides those slimy little creatures in your garden. A slug is a mass unit. There's your mass. So what is our formula? F sub W, that's weight, is equal to mg. Mass, 12.0 slugs. But what do we use for our G now? Yes, 32.2 what units? Don't ever just give me a number. Feet per second squared. Perfect. Okay. And I think I'll need some calculator help on that one. Looks like it's going to be about 350 or so. Say again? A little louder. 386. Point what? 4. So let's round that to 386. What unit? Pounds, exactly. In the U.S. customary, we measure forces or weights in pounds. Thankfully, the scale didn't say that this morning, so good deal. So I have a mass of less than 12 slugs. Okay. 386 pounds is the weight of 12 slugs. All right, on the surface of the earth, by the way. That's what we'll just about always assume. All right, now, any questions before we move on? We finally get, we've been using this slide just because it had a lot of white space on it, but we're finally going to get to the, what this figure is about. Okay? This is a brick. Okay, I just noticed what the caption said. This brick is sitting on a table. Pretty hefty little brick, right? Now, would you say the brick has no force on it? Okay? No, I wouldn't say that either, because you know it has weight. If you pick up a brick, you know it's got weight. But it's sitting there on the table, not moving. Now, since it's not moving, meaning it has no acceleration, has no change of velocity, that means its net force is zero. Net force is zero because it's sitting there, okay? But we know that the weight of the brick is significant, F sub W, and that's equal to mg, right? Okay? What's keeping that brick from moving if it has that much weight? The table is pushing up on that brick with what we call a normal force. Now, normal doesn't mean as opposed to abnormal. Normal means perpendicular. Okay, in physics and in math, normal quite often means perpendicular, not all. How are you feeling today? All normal. Yeah, that's not what we mean. We mean perpendicular. Okay. Now, does that make sense? Well, if I were to get up and stand on the table here, and y'all were very observant, I don't know, it's a pretty strong table. Okay, so you might not notice anything. But if I were to take a 1x6 and lay across here, a plank, and then try to get up on that and step on it, what's going to happen? You said it broke? Is that what you said? Okay, no. Okay, he just lost 15 points. Okay. No, okay. All right. It would definitely sag, wouldn't it? It might even break. Odds are it might break, okay? But it would sag big time. Why? Because its normal force wasn't equal to my weight. It couldn't support that. This table feels pretty strong here. I think it could support my weight. And therefore, it would push up on me with, we won't say how many pounds. Okay. This morning it was 212, I believe. Okay. So, if the brick is sitting on the table and not moving, that means gravity is certainly pulling down with the force of its weight, mg, whatever that happens to be for the brick, whereas the table is pushing up with an equal but opposite normal force. That's what gives it zero acceleration. That's why the brick's not moving. If the table were sagging, then that means the weight exceeded the normal force, okay, until it reached some sort of equilibrium there, okay? So that's what we're talking about here, and if you'll follow in your book, the normal force is always perpendicular to the surface, okay? Now, I'm trying to follow in the book since they don't have any PowerPoint slides for the lecture. Make sure I'm going to cover everything here. Note that the mass of the object remains the same, but the weight varies. Okay, what are they talking about here? Yeah, okay. Same thing I was talking about before. I just don't see why they come up with it out of the blue here. For example, an astronaut of mass 75.0 kilograms has a weight of, okay, so they're just going back to that. So let's do that since they brought it up here. So here's an astronaut who has a mass of 75.0 kilograms, okay? What is his weight if he's on the surface of the earth? What's F sub W? M times G. M is 75.0 kilograms. And G, what G do you use? SI. Second? SI. Yeah, the SI, and what is that? 9.80, what units? meters per second squared. Okay? Always have units with your numbers. So if you got a calculator, punch that in for me. It's going to be something less than 750. What's it going to be? A little louder? Okay, 735, is that on the nose pretty much? Okay, and what units? Newtons. Kilogram meter per second squared, which is a unit. Okay, now, if the astronaut lands on the moon, where the acceleration due to gravity is less than that of the Earth, the astronaut will still have the same mass, unless he lost some mass on the way to the moon, which we hope he didn't. Okay, or she didn't. Same mass, but will weigh significantly less. In fact, it's about 1/6. Okay. Okay. So the following example shows the weight on the moon. Find the weight of a 75.0 kilogram astronaut's weight on the moon, where G on the moon, see this is G on Earth, I'll put E for Earth, where G on the moon is 1.63 meters per second squared. Quite a bit less than it is on Earth. So what's the astronaut's weight? F sub W is equal to 75.0 kilograms, same mass, but now the G is 1.63 meters per second squared. And someone with a calculator punch that in for me. What you get? A little louder. 122 what? Newtons. Hey, guess what? Forget about all this dieting. Here's a great weight loss plan. Go to the moon. Okay? You're guaranteed to lose weight. You haven't lost any mass, but you lose weight. Unfortunately, when you come back, you still, unless you lost some mass, you're going to have the same weight as when you left. So, pretty simple weight loss plan, right? All right, and they got 122 also. Okay. The mass didn't change. So if you want to do a mass loss plan, yeah, you got to work on that one. Okay. Weight loss plan, just leave the orbit of the Earth. Okay. That's simple, huh? Okay. Now, they have another little blurb here at the bottom of page 130 on mass versus volume. Now, I don't see how many people are going to confuse those. People do confuse mass and weight. Because we talk about pounds as that's how much of it is. No, that's a force. Mass kilograms, that's how much of it is. That's the mass. We never use slug in the U.S. customary system. We treat it as if pounds is mass. It's not. It's a weight. Slug is the mass. And in the metric system or SI system, we use newtons for weight. That's not mass, it's newton. Now, mass versus volume, well, volume is what space it takes up, okay? What capacity it has, okay? That's all. Now, there's a few things that might make it easy to confuse. Water, the most common substance on the surface of the Earth, right? 2/3, 3/4 of the Earth's surface is covered with water, right? Most common material. It's 1 gram of water has exactly a volume of 1 cubic centimeter of water, or 1 milliliter of water. So, in that sense, you might get them confused because the numbers are the same. But that's because the density of water is 1.00 grams per cubic centimeter. That's how they define what a gram was, okay? Because when the French were setting up the metric system, They determined what a meter was, took 100th of that, made a centimeter. That's, by the way, about your width of your little fingernail. They didn't use that, but that's about what it is. And then if you do a cube of that high, that wide, and that deep, little bitty sugar cube that's not going to sweeten anything, that would be 1 cubic centimeter. That's going to have a mass of 1 gram. If it's water, 1 gram of water is 1 cubic centimeter of water. And a person's volume stays about the same when you go to the moon. It's not going to change a lot. It might change slightly because you're under less pressure on the surface of the moon, and therefore you may blow up a little bit, okay? But we're not getting into that now. So anyway, there's a problem set on page 131. I would do either 1 or 3 or both. Either any of the odds 5 through 9 and any of the odds 11 through 29. Again, just a bunch of problems to let you practice with mass and weight. All right. Now, they do have in the blurb on page 131, why they chose to put it here, I'm not really sure, but let me just write this down for you. I'll erase these so you don't get them confused. They have a little sketch here, okay? Here they have a rectangle. I don't draw very good rectangles. Okay, let's just pretend those are straight lines, big pretense, right? And they tell us the length of that rectangle is 4.0 centimeters. Okay? We don't know the width of the rectangle, but we do know the area of the rectangle is 12 square centimeters. Could you tell me what the width is? Okay, here's your basic formula. Area of a rectangle is equal to length times width. We know area, we know length, we don't know width, so we could divide both sides by length. Lengths go out here, and width would equal area divided by length, which would be 12 square centimeters divided by 4.0 centimeters. What would that give us? 3.0, and centimeters will go in centimeters squared, centimeter times, so the width would be 3 centimeters. Obviously, mine is not to scale, because my width looks a lot less than half of the 4. The one in the book is even worse, okay? So these things don't have to be to scale, okay? But that all the pictures are there for you to give you an idea how to go with it. Okay. I don't know why they put it here, but they did. I guess they were talking about mass versus volume. And your volume doesn't change either when you get into a different gravitational field, but the mass doesn't change. The weight would change. All right. So let's move on to friction. Okay? Now, we kind of talked about this before a little bit. I think we did. Yeah, when we were talking about the airplane flying and stuff like that. And I may have even pushed on something. Okay? Okay. I pushed with more force than what this weighs, but the problem is there's friction in the floor. So here's this, I don't know what my toys are anymore, front end loader, let's call it, okay? Pushing on this block here, okay? Now it's pushing with a force in this direction. That's what these strange looking arrows here are showing. However, this thing doesn't just slide. Now if that were, did y'all watch the Olympics earlier this winter? Those people on the ice skating and stuff like this, hardly looks like any friction at all. Okay? Don't put me out there. Okay. So this is a block on solid ice. Not even close. It is going to be very difficult to push with that. Why? Because there's friction. Now, why is there friction? Let's take just a little spot here, just some little spot, and magnify it like crazy. And you see that surface isn't perfectly flat. If you rub your hand across the table here, you'll feel there's a little bit of a texture to it. Okay, you can feel a little bit of different things. I can look at that, and just the fact that the window, the reflection of the window, I don't see a perfect window. I see a light blob and a dark border, but it's not perfect. That's because it's not a perfectly flat surface. If that were perfectly flat sheet ice, then I would do this and I'd just slide. I'd put a pencil there and push, and it'd just slide almost without any interruption at all. Okay? But it's not. There is some texture there. And if this is a concrete slab down here, there's a lot of texture there. A whole lot of texture. Unless they really polish this. Okay? And this block here, I don't know what it's a block of, but it is not perfectly solid either. And if you were looking at it microscopically, you would see there's peaks and valleys here, and there's peaks and valleys up here too. And this situation here is not going to be so awfully hard to move because this peak is just barely touching that one. But if this one, the pressure here gets down into here and you push, that's going to be hard to move. Okay? And the odds are there's going to be just about as many of these as there are here. See, this one over here is down in a valley. They just happen to show these two peaks are right on top of each other. That's not going to be too hard to move. Okay? But in general, it will be. And the rougher the surface, the harder it is to move, right? If this is a fairly slick floor, not too bad. But if this were rough concrete and I tried to push this along here, this is still sort of hard to move. But if I do that on really rough concrete, really hard to slide. I want to pick it up and move it, okay? Well, that's what's happening. There's always some frictional loss, okay? Friction always opposes the motion, okay? If I'm pushing this way on this, friction is pushing that way. If I'm pulling this way, friction's going this way. It always opposes the motion. Always. Okay? Now, let's get to the physics of it. Okay? Friction is a force that always acts parallel to the surface. Remember, we had a normal force before that was perpendicular to the surface. Friction always is parallel to the surface in contact and opposite in the direction of the motion. Okay? So, what if I had a big old crate here? This is a big old crate. Okay? And I go to push on it, and I can't move it. Okay? I push a little bit, and I push this way, the effort force. The friction force is opposing me, always opposite. And if I can't move that, no matter how hard I push, I increase my force. If it still doesn't move, then it's just pushing back on me with a greater friction force. Because the net force is not, that's the trouble with friction. It varies, and this is what we call static friction. Probably shouldn't get into dumb stories like this, but the oh boy, I don't remember what year it was now. But anyway, we moved to a new house, okay? And my wife likes old things, thank goodness, because I'm older than she is. So anyway, she likes antique type things. This is sounding really bad, isn't it? Okay, it was a 1930s house, but some previous owner had built an extension on the back of it, and they didn't do a good job tying it in with the other one. And the house was on a hillside like this. The main house was on a fairly flat thing. Front yard fell off, backyard was like this. When they built into the backyard, they made it look squatty because the backyard was coming down like that. And the looks were one thing, but more important to that to me was the hydraulic pressure of rain coming off here, pushing against that wall, back wall of the house. I said, and then too, they had the soil right up to the windowsill almost. So you had almost soil to ground contact on the wood, soil to wood contact. You don't like that in the South because of termites. Now sure, they probably use pressure treated lumber, which would poison the termites, but guess what? That the treatment leaches out over time, and over time, the termites are going to win, okay? So I told my wife, we were looking at the house, I said, well, if we buy this one, I really think we're going to have to do some stuff in the backyard to do a berm or something to run the water away from the wall of the house, but also to lower that till you didn't have any soil to wood contact. And then my wife said, well, good, I wanted a patio anyway. Oh no, that's a lot more digging than I had in mind, okay? So that summer, it was the summer after I started teaching at Old Bessemer State Technical College, which is the Bessemer campus of Lawson State now, and I didn't have but 2 mini-term classes for 5 weeks, and then I was off the rest of the summer. And I was off, half the days of the summer because I only taught either Monday, Wednesday, or Tuesday, Thursday. So I had some time off, so we started working on digging out the patio. She took a hose and outlined the area that she wanted the patio to be. I thought, uh-oh, I'm in deep trouble now. So I thought, I'll see if she'll help me dig. She did. The hose came in some, Okay. If I'm remembering right, you're Mary, right? Okay. Have I had you in class before? Yeah, I thought so. Okay. When I saw your name, I thought either lots of folks have this very similar name, or okay. So you're here for the first time. All right. Good deal. Okay. So now we're up to 2, 4, 6, 8, 9. Yeah, okay. All right. So anyway, we got to digging on the patio. And somewhere about midway through the patio, and by the way, the depth we're having to dig, it started out being fairly shallow, but because the soil level was growing, we had me digging way back here, we got up to it's about like this in the deepest place. Well, when I was digging somewhere back there, I ran into this rock. I mean, I think I would call it a boulder, okay? And I dug and dug and dug around and around and around, and I was trying to get that thing out of the ground. I couldn't. I used cheater bars. I used everything I could think of. I had a pick, shovel. I could not get it to budge, okay? Because the harder I pushed, still didn't budge, the greater the friction pushed against me. Pushed a little bit, it pushed a little. You couldn't sense it, but it wasn't moving, and it wasn't exerting any more force than I exerted because it was just sitting there. So that's called the static friction, okay? Static friction varies according to the amount you're pushing on it. And that's what they're representing here. Twice as big of object here is going to have twice the force. It still have twice the friction if it's not moving, okay? I find this a little bit artificial, their illustration here, but that is called static friction. Now, there's another form of friction, and that's called kinetic friction. And the word kinetic means motion. Have y'all ever heard of kinesiology? The science of motion, of moving, okay? Now, let's take this table, for instance, okay? I'm going to pull on the table, okay? I can pull a little bit, and as long as it doesn't move, I'm being resisted by the force of static friction because it's not moving. And I pull a little, and it's staying where it is, so the static friction is exactly enough to counter my pull. My pull's this way, the static friction's that way. When I finally get it to move, it seems to move more easily. And that's because kinetic friction is generally less than the maximum static friction. And it goes back to this, okay? Once I've got it moving, okay, to begin with, these low places here are stuck down in the low places there. That's static friction. It's hard to get it to move. But when it does start moving, now they're just sort of skimming over the peaks, and it's easier to move. So the kinetic friction is usually less than the maximum static friction, okay? And that's what they say here in the text, okay? For those who do have this, friction is a force that always acts parallel to the surface in contact and opposite in the direction of the motion, if you're trying to get it to move. Number two, static friction is greater, the maximum static friction is greater than the kinetic friction. I want to say maximum because if I pull just a little, there's a little bit of static friction, but it's not moving. The maximum static friction is greater than the kinetic friction. And friction increases as the force between the surface increases. Okay? And this kind of makes sense. Okay? Now, where is the friction here? The only thing touching the floor down there are the feet. Okay? And it looks like there's 4 feet, 2 on this leg and 2 on that leg. That seems to be what it is. So all the friction is between the foot and the floor, right? Now, I'm going to pull on this, and I can move it. It's not that bad. But if I get, I've got a great memory, it's just short. Chris here, right? Okay. To stand or sit on the table or lay on the table. He's lazy, he probably won't lay down on the table. And then I go to pull on it. Easier or harder? Harder. Because what? He's pushing down on that thing, and those grooves are getting down in those holes, and it's going to be harder to get it to move, right? So the third point here they made about static friction, about friction is friction increases as the force between the surfaces increase. So if he puts more, and what's the force? Weight. If you put his weight on there in addition to the table's weight, then it's going to be harder because the friction is going to be greater. Okay. Very good. Okay. Now, the characteristics of friction, now I wish they had a good PowerPoint. They don't. Okay. Here is a formula that relates, an equation that relates this. Okay? F sub F, that is your frictional force. The resistive force, the blue arrow in this direction, okay, is equal to mu times F sub n. Okay? Now that just sort of comes out of the blue for you, right? Well, here's what that means. Okay? The frictional force, the static force here, that's the F sub F, is equal to mu. Mu is called the coefficient of friction. Okay? And there's 2 kinds. Static or kinetic. Okay? The stationary friction or the moving friction. So there's two of those. This is just in general. And what's the normal force? The force that is perpendicular to the surface. So the normal force for this table now is the weight of the table, because that's what's on the floor, right? If I increase that normal force by putting Chris on top of here, okay, then the friction force increases, because the coefficient stays the same. What the coefficient is the relationship between the foot and the floor, okay? The floor is pretty slick. That's why it was fairly easy for me to move the table. The feet, I haven't looked at them, but my guess is they're fairly slick too, so I can move it. But there's still some friction there. With more force on it, in other words, Chris's weight added to the weight of the table, then the frictional force increases. Okay? So F sub F is equal to mu times F sub n. Now this F sub n is not net force, this is normal force. Sorry we use the same letters for several things, but that's your normal force. Okay? And mu is your coefficient of friction. And again, you have, and I wish they had these here, but I don't think they do. No, they don't. Let me jot down a few of these for you. Okay? It irritates me that we don't have a better. I've got to call the company and see if they do have a lecture PowerPoint. All they have is the image PowerPoint that I've been able to find so far. Okay? I think I'll just read these. It's going to take way too much to write. Okay? Steel on steel. Okay? I'm guessing that's a steel foot there, and let's say it's on a steel floor here. Okay? The static friction, 0.58. The kinetic friction, 0.20. I mean, 0.20. Static friction much greater than the kinetic friction, because once you get the steel moving, the friction goes down. What if you lubricate the steel? What is a good lubricant? Say again? Water can be, okay, but where do you have some steel on steel friction? You probably, say again?
Would it be like your brakes?
Your brakes? They're coming close. I'd say the car engine. The car is steel, the engine's steel, steel parts are moving on steel parts. You don't want friction in there. You want them on your brakes, but you don't want them on the steel part. So, yeah, pretty significant, but if you put, what do you use as a lubricant there? Oil or grease, either one. Grease on the bearings and oil in the inside. Steel on steel lubricated. Static friction goes down to 0.13, and kinetic friction is very close to 0.13. Now remember, and maybe I said this wrong. In fact, they said it wrong. The static friction, let me say this again. Mu sub s, that's the coefficient of static friction, is always greater than or equal to mu sub k, which is the kinetic friction. It's not just always greater. The book made it sound that way. It's greater than or equal to. And for lubricated steel, it's almost the same. Glass on glass, 0.95 static, 0.40 kinetic. So much less for kinetic. Hardwood on hardwood, that would be me sliding that over a wood floor. Okay? 0.40 static, 0.25 kinetic. Steel on concrete, goodness gracious. They don't even list one for static, but it's about 0.30 for static, for kinetic. Aluminum on aluminum, these are really strange. They don't list one for kinetic, but they do list it for static, 1.9. So that's a pretty big number. Rubber on dry concrete, 2.0. Is that good, bad, or indifferent? I want my car tire to have great friction between it and the road. Why? If it didn't, I step on the gas and it spins. Kinetic friction. I want it to have a very high static friction so that it doesn't. Or when I turn a corner, I want it to make my car turn. I don't want it to slide out into the tree over there. You don't want skidding. You don't want slippage. You want that rubber on hard concrete, dry concrete, to be a large coefficient of static friction. But when it rains, the kinetic friction drops by half, about 1.0. But if it's rubber on wet concrete, now let's go back to the previous slide. If the concrete's wet, then most of this indentation here is filled with water. And now, even though water won't support this, it still lubricates a little bit, and now the coefficient is much less. Now, what if that is coated with ice? Okay, there you go, into the ditch. Was anyone around, how many years ago was that now, when they had what they call the snowpocalypse? Yeah, remember that one when I happened to be at the Kirkland Clinic that day with a doctor's appointment, and when everything was over with, I looked outside. It had been a light dusting of snow going in. They said no problem. Before my appointment was over with, it was snowing like crazy. The ground had been very cold that night before. That's why they weren't expecting much snow. Here in the South, if it gets too cold to snow, well, it had gotten very cold that night, but then it did snow, so that snow went right to ice, especially once the first car ran over it. And then the roads were a skating rink, okay? And it was horrendous, okay? Because then your valleys get filled with ice and everything slides over it, okay? So rubber on wet concrete, 1.5 static friction, 0.97 kinetic friction, much less. So that's why when the roads are wet, you're going to be a lot more likely to slide. Aluminum on wet snow, 0.4 was your static friction. That's not very much. And 0.02 is kinetic friction. And if y'all notice the snowboarders, if you watch the Olympics and the skiers, they had very slick skis, and then they waxed them, okay, trying to get that to scoot over the snow much more easily without, especially those on the downhill and the slalom, they were wanting maximum speed. Steel on Teflon, 0.04, 0.04. Very slick, okay? Now, they do give some hints here to reduce kinetic friction. When you want it reduced, like in your car engine, you don't want friction there, okay? Use smoother surfaces, and quite often those will be machine surfaces. The ball bearings in your wheel, the tire, those are just as slick, smooth bearings as you can get. No barbs or anything on those, okay? Use lubrication to provide a thin film between the surfaces, okay? And that previous slide, when you get oil in there, yeah, let's do this one. Put oil in between there, that's really slick then. Or grease, even slicker, okay? Use Teflon to greatly reduce friction between the surfaces when oil lubricant is not desirable, as in electric motors. Now, where was Teflon? I don't know if it's originally used, but where first use I remember of Teflon was in non-stick pans. The Teflon. Now they have Teflon and all sorts of better things, but Teflon was used then. And you don't usually use oil in electric motors, but you could use something like Teflon. Substitute rolling friction for sliding friction. You really want that to happen. Rolling friction is actually static rather than sliding. And that's what ball bearings do, rolling rather than sliding. All right, so let's do an example with friction. So let's find, actually, it's going to do a lot like this one. So I'm going to clear my writing here. All right. What we have here is this F sub W here is going to be 530 newtons. Okay? The normal force, what you reckon it's going to be? Is that brick falling through the table? No. Is it flying off the table? No. So what do you reckon the normal force is going to be? 530 newtons. The net force is going to be 0. Right. Okay. Now, a force of 170 newtons, and this is no longer a brick, this is a wooden box now. And this isn't a table, this is a floor. Okay? Sliding on a wooden floor. A force of 170 newtons is needed to keep this 530 newton wooden box sliding on the wooden floor. Okay? So you're pushing in this direction with 170 newtons. And that keeps it sliding just barely on the wooden floor. Now, if it just keeps it sliding without increasing the speed or decreasing the speed, just keeps it sliding, that means the frictional force must be opposite to the motion and also 170 newtons. Because if it was anything less, then it would be accelerating, right? Because it would be a net force, and it wouldn't just be keeping it moving if, you know. So just looking at this, you can't tell whether that's static or kinetic. They tell us it's kinetic, okay? Because you're keeping it sliding on the wooden floor. The question is, what is the coefficient of kinetic friction? Okay? Well, what was the formula for kinetic friction? Or friction in general? F sub F, and I'm going to make that kinetic friction, is equal to mu sub K times F sub N. Now remember, that F sub N is your normal force, not your net force. Okay? They've already told you what this is. That is your kinetic friction here, 170 newtons. Mu sub K, coefficient due to kinetic friction, times the normal force, which is 530 newtons. Well, let's divide both sides by 530 newtons. And what is your normal force? These go out here. What's 170 divided by 530? And notice your mu sub K is just a pure constant. No units associated with it. It's just a ratio. As the newtons go out, you could even make the zeros go out. That's fine too. 17 divided by 5.3. Mu sub K for wood on wood that would be what? 17 divided by 53 here. 170 divided by 530. Anyone get it? Get an answer? Anybody? Say again? 0.32? Okay. And let's see, yeah, we probably can't do any better than that. And that would be a dimensionless quantity. Well, let's see what we said, kinetic friction of wood on wood. Doesn't have to be the same, but let's see if we can find it. Hardwood on hardwood, they had 0.25. So yeah, that's not far off. Okay. Yep, 0.32. And it has no units because the force units always cancel out. Now, someone mentioned, I think it was Dana mentioned braking. When you're driving down the road and you want the car to stop, you press on the brake. Well, what's happening then? Now, it may vary in different kinds of cars, but what you have is a pad on another, and sometimes they're called rotors, okay, and these both have grit on them, as in corundum or something like that, and they rub against each other, lots of those hills and valleys there, and it does bring the car to a stop, okay? And that's what you want it to do, okay? Now, if the brake pad wears out or gets slick, you're not going to have as good a braking power, and you have to take it in and have the brakes resurfaced or new brake pads put on or whatever. There is a connection here between friction and anti-lock brakes, and that connection is you want those brake pads to be static. You don't want them to be sliding because the coefficient of sliding friction is less than or equal to that of static friction. So you want it to stay static. And you want your tire to be static on the road. If you ever start slipping, then what anti-lock braking does, it eases off the brake so that you go back to a static state. And that's exactly what anti-lock braking does in your car. If you do start sliding, then it eases off. Even though you're pushing with the same amount, it mechanically eases off so you go back to static friction. So that was your little physics connection there. Okay? Your problems here, the answers in the back are your odd numbers, so do any of the problems 5.4 between 1 and 15. Any of the odds between 1 and 15. Okay? And there's another little blurb here on new technologies, hydrophobic metals, that's reducing frictions, and that's what Teflon is one. It is hydrophobic, meaning it resists water, okay? Anyway, you can read that if you'd like. I don't think that's essential for what y'all are going into, so I'll just go on over that. All right. Let's see our next slide here. I don't see this figure in the book, so I can't really speak to it, but I don't make a lot of sense out of this figure. Oh, there it is. Okay, we'll get to that later then. I was hoping they'd have one of these figures, but they don't. Okay, so let's go back to one like this. I'm sorry, I wish the PowerPoints were better. I'll see what I can find out if I can ever have any time in the office. Section 5.5 is talking about total forces in one dimension. Okay? In the examples used to illustrate the law of acceleration, we discuss only the total forces. We need to remember that forces are vectors. What does a vector have? Two quantities. Magnitude and direction. A vector has magnitude and direction. A scalar only has magnitude. Okay? Oh, and by the way, I didn't mention this after Mary came in. If you want to see and hear last week's class, you can go to Blackboard. You know how to get to that. And I just can't tell you right now. Since several of you are new now, I want to pause. I don't want to end the show, but I guess I'm going to have to. So I'm going to end the show for right now. We'll discard this. Okay. I want to go to Blackboard so I can show y'all. There it is. Okay. To go to Blackboard, I have an icon for it, but however you get there. And I have to log into it. Okay. Y'all don't have this many classes. And I know you are glad you don't have that many classes. Here is this one. Like I said, somebody else came up with this thing over here. The syllabus is under that blue tab. There's the syllabus. Okay. Hi, here it is. Class handouts and more. Well, I'm not going to be handing out anything, but it's the closest I could get to content. So here on the class handouts and more, there's my locator card that shows where I am Monday through Friday, which campus, which class I'm in, when I'm in the office, when blah, blah, blah. Here are all the PowerPoints that we are having. And here's the Physics 112 YouTube videos. You go and click on that. In fact, I'll do it right now. And, okay, there's the one class we did last Wednesday. I named it syllabus, but it has more than syllabus. Locator card, we talked about safety, and we talked about, we got started in this chapter. So you go and just click on that, and you'll see and hear. You won't see me, thank goodness, but you'll see and hear everything that's projected on the board and everything we say about it. Okay, so I'll get out of that, and we'll go back to this. And we'll go to this slide. Okay. This was the one where I was going to do examples on section 5.5. Two workers are pushing in the same direction to the right on a crate. So let's say we're going to, let me get my pen color back. Okay. They're pushing to the right in the same direction on a crate. Looks like a pretty good sized crate. So here's the two guys. They look like guys anyway, pushing on this crate. One's pushing up here, and then the shorter guy's pushing down here. Okay. Okay. And they're both pushing on the crate. Okay. Pretty ugly drawing, right? Pushing against the crate. The force exerted by one worker, let's say the little guy here, is pushing with a force of 150 newtons. No, 150 pounds. And that zero is significant. The force exerted by the other is 175 pounds. Okay? The force exerted, okay, got it. Find the net force exerted. That's pretty simple. What would it be? This now is net force, not normal force. What would that be? Add the two together, right? 225, no, 325. I can't add. 325 pounds. Okay? That's the net force. Both forces act in the same direction, so the total force is the sum of the two, and that's 325 pounds to the right. Okay? The same two workers push on the crate to the right. The motion is opposed by a static frictional force of 300 pounds. That is not true. Okay, I'm sorry. It would have to be kinetic friction. They say the friction force here in the opposite direction is 300 pounds. Well, if that was 300 pounds, then they are pushing with a greater force than that, and it would be moving. It would be accelerating. Then it wouldn't be static. It would be kinetic friction. Okay? But they say it's moving. Just ignore the word static frictional force and make it kinetic frictional force. And that 300 has a significant zero there. Find the net force. Well, they're pushing 325 to the right. This is 300 to the left because friction force always opposes the direction of motion. So the net force, okay, this is another net force here, then would be 25 pounds. Okay? Now, and that would be 25 pounds to the right, because this force is greater than that. Now, I want to point something out to you here. Remember all the talk about significant digits, okay? When you're adding and subtracting, you don't keep the same number of significant digits. Multiplying and dividing, you do. Here, you can't get more or less precise than a pound. So you don't put a zero at the end of that one and make it 25.0 pounds. No, you don't do that when you're adding and subtracting. Subtracting or adding, you keep the same unit that you had going in. So that's why it's just 25 pounds to the right. Okay? And frankly, that would be kinetic friction, kinetic, because the net force is to the right. Now, the crate in example 2 has a mass of 5.00 slugs. Okay? So the mass of this crate, 5.00 slugs. Okay? What is the acceleration when the workers are pushing against the frictional force? Well, the net force is 25 pounds, right? This is the mass of the crate. So what would be the acceleration? Remember our basic formula there for net force? What was it? Newton's second law? Mass times acceleration. We know net force, we know mass, we're looking for acceleration. This is the one we're looking for. So you can either divide and then plug. I call it chug and plug or plug and chug. It doesn't matter which one. Let's just go on and divide by mass, both sides. So your acceleration would be the net force, I shouldn't probably put that on, divided by mass, okay, which would be 25 pounds, that's only two significant digits, divided by 5.00 slugs, and what would that be? 5.0, because you can't get more precision out than you had in. And what's the unit? What is a pound, by the way? A pound is a slug foot per second squared. So you divide out the slugs, and this is feet per second squared. That is quite an acceleration. You're not going to be able to maintain it for long because it would get to be very, very fast. Okay? So again, when you subtract, you don't conserve significant digits. You conserve your basic unit. So you wound up with 2 significant digits there. Even though your mass had 3, when you do your acceleration, you have to only use 2. 5.0 feet per second squared. All right. Let's clear that out of the way. Two workers push in the same direction on a large pallet. The force exerted by one worker is 645 newtons. Okay, it didn't give a direction here, so let's just have it this way. So this will be 645 newtons. The force exerted by the other worker is even greater. That's 755 newtons. So you have two forces going in that direction. The motion is opposed by a frictional force of 1175 newtons. 1175 newtons. Find the net force. How would you do this? Add the two forces you're exerting. That would be 645 plus 755. And I believe that comes up to 1400 newtons, doesn't it? Okay. Subtract from that your 1175 frictional force, and that gives you 225 newtons, right? Net force of 200. So there's your net force now. Okay? Yep, and that's what they got. Oh, that's all we were asked to do. Find the net force. That was pretty easy, right? All right, problem set 5.5. Do any of the odds 1 through 13. Okay. Now, 5.6, law of action and reaction. That's what this figure was trying to show, and it's a fairly I do not like this figure at all, okay? If it is trying to show law of action and reaction, that's Newton's third law, by the way, they're always equal and opposite, okay? Always equal and opposite. This is showing this one's much greater than that one, okay? Not the case. Not the case at all. Now, here may be the case. This is just one of the forces, okay? This isn't showing action-reaction per se. It's involved with it, but it's not just showing that, okay? And this is what kind of drives me nuts about this one. Because by definition, the law of action and reaction, they're always equal and opposite. So if you got your book and look on that law of action and reaction, Newton's third law, for every force applied by an object A to an object B, that would be action, there is an equal but opposite force exerted by object B on object A. That's the reaction. So therefore, this is not a picture of action-reaction. Okay? The one below it is, okay? The one above it is not. Now, what is going on in this one is the net force of the wheel on the road. Okay? The wheel here, the road there. You have static friction between the two. That means your car isn't spinning its wheels. You're not spinning the wheel to take off. You've got static friction there. If you're pushing back against the road with 100 pounds of force, but the engine is pushing ahead with 500 pounds of force, that means you're going to accelerate. Okay? Actually, I say that wrong. The road on the tire, the frictional force is 100 pounds. The tire on the road is 500 pounds, which means you have a net force this way of 400 pounds, meaning you're going to accelerate. Okay? You're not going to maintain that kind of difference for long because that's an enormous acceleration. Huge. So that'll get you started, but then after you started, that acceleration will decline significantly. So that's not a picture of action-reaction. Figure 511 is, but that's not shown on the slide. I don't know what figure 510 was trying to show. Oh, that may have been one of the problems. No. I don't see it there either. So, anyway. This, however, is a illustration of action-reaction. Now, I don't like guns in general, handguns in particular. If you've ever fired a weapon, have you? Any of you have, okay? Rifle, shotgun, pistol. Pistol and rifle, okay? Now, if you fired a pistol before, you know that it does this. And that's what makes pistols notoriously inaccurate. Okay, number one, you've got a very short barrel there. You're sighting down with just a little bit of error, you're not even going to come close. If I was trying to hit that outlet plug, that silver plug there, the stainless steel plug there on the thing, with a pistol, and I'm not a really good shot, are you? Okay. Do you think from here you would hit that?
Well, the more practice you have with your gun, the better.
What's that?
Like the more practice you have, like
yeah, the better you get at it. But from my understanding is you're going to be hard pressed to hit that.
Right.
Now with a rifle, you can do it. You got much longer sighting and stuff like this. Pistols are notoriously inaccurate. And therefore, this is political, I shouldn't get into this. When they're talking about arming teachers in school, I assume that's with pistols, right? It would have to be, right? But what are those guys coming into the schools with? Automatic weapons! You don't have to aim those. You just wipe them out. So the odds are, if the guy came in shooting and I went to shoot him, I may hit Mary. Okay, I don't want to hit Mary. So I'm not going to shoot. If anyone, in fact, I think that's how police are supposed to do anyway, and I think it's in the military too. If there's civilians in the way, you don't shoot. So guess what? Room full of kids, one shooter. I've got a pistol up here. Unless the kids are all back here and I just got him in front of me, I can't shoot. Okay? Because I might hit one of the kids. Okay? Y'all are kids now, right? Okay. You feel young. You're younger than I am. So yeah, but here's what we got. And one of the reasons is that they're very notorious. You pull on the trigger, it always recoils. Okay? And if it's just your arm there, there's not a lot to keep from it. Because the force with which that bullet is fired out of that, the same force is pushing back on you. So when you're using a rifle, what you do, the rifle is much more massive, so it has more inertia, so you can hold it more steady. plus you have your whole body weight here. Now, if you hold it away from your shoulder, what are you going to have? A bruised shoulder or a dislocated shoulder, because it's going to kick back and do that. But you hold it snug up against your shoulder, and then you have your mass and the rifle's mass much more steady and stable, okay, than a pistol. Pistols are notoriously inaccurate. Would you say that's true? Yeah. You just can't do it. There's nothing to aim through, and then, yeah. So, but this is absolutely true. The action on the bullet, the force of the bullet out of the thing is the same as the force on the reaction on the hand. And you will sense that. Of course, you, the gun, your hand, everything is a lot more massive than the bullet, but still the forces are equal and opposite. Okay? And remember, forces are mass times acceleration. Huge mass here, very small acceleration. Very small mass here, enormous acceleration. Okay? The forces are equal and opposite. So, to me, the whole argument of arming teachers is nuts. Now, my wife is much more practical than I am. She says, think about the insurance that it's going to cost the school. If they start having to pay one parent suing a teacher because she fired at the guy, the bullet ricocheted off his weapon, hit the student, they sue the student, the teacher. So the school has to have that kind of insurance. I don't think that will ever fly. Okay? She didn't care about accuracy and stuff like this. She said insurance, I don't see how they're going to do it. But anyway, that's not physics. Okay, that's politics. Okay. Let's get away from that. Okay. Now, this is another rather dumb illustration. Okay? And we don't have a lot of time left, so I think I'll use the end of it. What was the first aircraft that man used to fly? Does anyone know? Are you thinking Wilbur and Orville? Think before them. What was the first aircraft that man flew? Does dirigible mean anything to you? Blimp? Balloon. That was the first, okay? And what you did there is a balloon, and this isn't exactly how they did it, but this sort of is the principle of it. Of course, they didn't blow up the balloon they used, but you blow up a balloon and then hold the end, and what you have is all that air pressure in the balloon. You open the end, and the balloon takes off. Now, typically it goes all over the place. Why is that? Because at the end you have a real floppy nozzle. So every time the nozzle moves in the direction the balloon moves. But that is propulsion. You have force this way, air moving this way, the balloon takes off and goes that way. The air blowing out of the balloon, the force of the air going out of the balloon is equal and opposite to the force on the balloon in the opposite direction. Okay? So that was our first thing. Then we came up with propeller-driven planes, and that's what Wilbur and Orville had. In that one, what you had, the propeller is pushing air this way, which forces the plane that way. Okay? It's pushing air here, and the plane goes that way. So that's propeller-driven aircraft. Then you move up to jet aircraft. Now, jet aircraft, you have the explosion going on in the jet engines, the exhaust going really fast in that way, and that's what propels the plane in this direction. Equal and opposite. The force this way, equal and opposite to the force this way. And then we have rocketry. And rocketry, the explosions, the exhaust pushing down, the rockets taking up. There's your balloon again. Okay? It's almost, the same type thing over and over. Okay, they show the shuttle launch here. Basically, it's almost exactly the thing that you have with a balloon, except much faster exhaust gases. We finished Chapter 5. I wasn't expecting to finish it tonight, so I don't have your test ready. So I will have your test ready next time. And you folks that weren't here last time, the people that were here really fixed you, didn't they? They wanted take-home test. So guess what? It's going to be a take-home test. You don't want a take-home test. Oh! So I will have your take-home test ready, and you can work on it over the weekend and get it back to me. All right. Now, what was next on the... well, we really don't have time for anything new. Any questions on Chapter 5? Things you can look at in Chapter 5 to study. There is a glossary that has some of these terms. I'm not going to do much of a word type thing for you. Most of what we're going to do is, I haven't seen the test bank, so I don't know. But there are some review questions here. There are 3 formulas given. There are review questions, multiple choice, some multiple choice, some not. I don't see where the answers are. I bet you they're in the back of the book too. And let's just see, are they, what do they give for that? Chapter 5 review questions. They give all the answers to review questions. So review questions, good to look at all 16 of those. And then review problems. They have all those answers as well. So any of those that you want to look at. You don't have to do them all, but do some of those. Okay? And then there's applied concepts. You can look at those too. Those are pretty interesting, it seems like, just reading this. So, and let's see if applied concepts. Yep, they have all those answers in the back too. So they're a little more involved. I doubt if we'll have questions like that. So I'll have ready for you next time your test on Chapter 5. Let's just see what's next. End show. Discard. Okay. Which chapter is next? Chapter 8. We skip 6 on momentum. We skip 7 on concurrent and parallel forces. And we move to Chapter 8, working energy. I knew that. Okay, so Chapter 8 is what we begin next time. I have your Chapter 6 test ready for you, and we will get started on Chapter 8, working energy. Okay? Any questions?
I have a question.
Yes.
Do you have a parking permit?
Oh.
Park out there, do you have to like a hang tag or anything?
Okay, what you need to do, yeah.
Yeah, like once you pay for your class, they'll give you
I'll pay for my class today.
Okay. Yeah.
Yeah.
Okay. Here on this campus, it's over on the West Campus, in the administration building. Do you know which one that is?
Yeah, I went there this afternoon because I had completed my registration and they added this class and then I couldn't pay for it online. I had to go to the office and
Right.
work.
Okay. Downstairs, you went upstairs to pay, right? Okay, downstairs, just about directly beneath that is where they do the parking decals, I think. Is that right? See, I'm on the Bessemer campus, so I don't know. Isn't that where it is?
Okay.
Oh, is it where you pay? Okay, up on the second floor? Okay, yeah. So go back there and tell them you need a decal. You don't have to pay for it since you're enrolled as a student. You may get a ticket.
Okay, that's what I was asking.
And I don't know how seriously they're doing now, but if you can go before this class starts, someone will be there to handle that. And yeah.
No, that's not.
Okay. Any other questions? Good question. Yes, ma'am.
When is our first exam?
I can't hear you.
When are we taking our first exam?
Oh, I'm giving it to you. I'll bring it on Wednesday, and it'll be a take-home test. Yeah. And you bring it back. I give you a week to work on it. So that gives you a weekend and a chance to ask questions on the next Monday in case you're uncertain about it.
So every test is going to be like a take-home test?
What's that?
Every test is a take-home test.
Every test will be a take-home test. Sorry about that. Okay. I know she was looking forward to in-class tests. Okay. We just don't have a lot of time. Okay. All right. So we'll start on chapter 8 next time. Good deal.